All right, principle 3, tackle the causes first and then the symptoms. This should go without saying, but actually in waterway management, in stormwater management, I think this is unfortunately a fairly common error. So one approach we often see applied is to take some ugly bit of channel like this and to then use some, revegetation and so rip out the concrete, put rock back in place and make it a more, natural landscape. That looks nicer, let's be honest, that looks a lot nicer. But in terms of the ecological response, studies all around the world, including from our good colleague Chris Walsh, but from a number of other studies all around the world, show the same thing, that if the catchment stressor, that is stormwater, is still being delivered, so we've still got this big change in flow regime, we've still got these injections of polluted water every time it rains, we're not going to see an ecological improvement. Yep, it looks nicer. And we've got a bit more riparian vegetation, so that's good. But we're not going to see an in-stream improvement in water quality or in ecological composition, because the driver of that degradation is still the same. We've still got this stormwater input. And similarly, if we have the idea that, oh, let's create these nice buffer strips, which we tend to use in rural areas, and they serve very well to protect against, for example, cattle or cropping impacts on waterways, and they can tend to be, a few tens of meters and still be quite effective. A lot of studies around the world show this. But if our urban input is, as is typically the case, delivered to the stream via pipes, they're going to completely bypass those riparian zones. And even if we were to break that pipe and release it at the top of the riparian zone, that flow regime would just rip through that area anyway and cause erosion. So using a buffer strip is not going to be effective. Again, it may improve the riparian environment, but it will actually not do a lot to help the stream, because the impact is essentially bypassing it. And to be honest, it will be difficult to maintain that riparian zone, because the changing flow regimes will cause that channel to deepen and widen, and we'll start seeing undercutting of the banks, etc. Okay, so flowing on from that, let's use that pun. Our fourth principle is to try to break the connection between impervious areas and the receiving waters. If we think about what we do when we urbanise, we build, create imperviousness, and then we deliberately connect it with hydraulically efficient drainage connections into the receiving water. We want to use techniques that essentially break that connection. That is not to say we don't have a way of dealing with the flows anymore, but that for your everyday flows, we have methods of retaining, using, infiltrating, etc., that water. And so it can be as simple as a swale instead of a constructed drainage system, or rainwater harvesting, as we've talked about before. And we'll talk a little bit about the other technologies available in a minute. All right, the fifth principle should go without saying: wherever possible, preserve the existing assets. Now, of course, there's an argument to do that for their intrinsic values, but really importantly, a stream, for example, in a natural state like that, if we can then protect it, will have really good nitrogen retention capacity, have good filtering capacity, etc. If we were to basically cover this over and replace it with a pipe, we don't have any of that service provided to us anymore. So we then have to build those services. We have to build wetlands or bioretention systems, which seems somewhat counterproductive and not very cost effective. The sixth principle is to integrate stormwater management into the landscape. I talked before about water sensitive urban design potentially providing a whole range of benefits. This is really important. In the end, water sensitive urban design has to make sense in a business case. We have to provide enough benefit to the community that the community is happy to pay for it, happy to contribute to maintaining it, etc., which means providing benefits in terms of aesthetics, etc. The seventh principle is, again, we captured this before, water sensitive urban design should be part of a broader approach to ecologically sustainable development. So think about transport, energy, etc. The eighth principle is about matching the treatment type for water quality to the pollutant type we have. So this diagram developed by Tony Wong and Peter Breen shows the types of particle sizes, so the classification of particle sizes, and then the treatment processes that are appropriate for each of those. And I give here some examples of the treatment systems, and we'll talk about those in a minute, that that facilitates those treatment processes. So as an example, if our aim was to remove dissolved nitrogen from water, using a gross pollutant trap would not be the solution, regardless of what the manufacturer might try to tell us. But equally, if I've got a whole lot of gross solids like litter, then I might want to install some systems capable of dealing that in an efficient way and in a way that's aesthetically not displeasing, before I then have my more fine focused treatment systems downstream. There's nothing worse than a lovely looking wetland that then gets filled with litter. And so we can think about a treatment train concept where we're treating coarse material, then a little bit finer, et cetera, et cetera. And so we go through a process, and there are a number of guides around the world that take us through how to design a treatment train from a water quality point of view. All right, principle 9, only 2 more to go. Principle 9 is to keep it cheap, simple and robust where possible. There are a number of reasons for this. The first is, by definition, if it costs a lot, it's going to be hard to make it everyday practice, and we're really not going to see improvements to our receiving waters if it doesn't become everyday practice that we apply on every urban surface, essentially, or for the runoff from every urban surface. But secondly, if we need really specialist contractors, then that's going to be difficult. So thinking about systems that are sort of simple, cheap and robust where we can. And of course, it depends on the urban form. It's not always going to be possible. This is a system I quite like in Brisbane, Australia, a bioretention system that really, it's now a good 25 years old or 20 years old. And it's been really quite robust, pretty simple, pretty easy to maintain, and works very, very well. All right, let's talk a little bit about the individual technologies under those, under water sensitive urban design. The first is the gross pollutant traps, or the litter traps. So these have a particular purpose, as we've described. They remove litter from waterways. They're usually very effective as a pre-treatment. They can be ugly. I would argue that some of those, something like this on the edge of a lake is not particularly attractive. Necessary, yes, but attractive, no. This one here, again, not very attractive. Some of them are much more subtly hidden, such as this system here. Sometimes they can be fairly low capital cost, but they can need a lot of maintenance, and that's something to consider. Sediment basins, these, as the name implies, are primarily targeting a removal of sediments. They're often used during the construction process and then perhaps turned into a wetland or the upstream part of a wetland. Because they tend to be steep-sided and deep, there's safety and aesthetic issues to consider. Rain gardens, these are perhaps if I have to have a favourite, they're perhaps my favourite of all of the stormwater control measures, because they're very flexible. They can take the form of a swale, they can take the form of a tree pit, of a garden. And so they potentially have really nice aesthetic outcomes. They're very effective overall in treatment performance. Arguably, they have the highest sort of treatment efficiency of all of the systems. And they can also be flexible in terms of performance, so they can promote exfiltration, or they can be lined if that needs to be the case. They may not be appropriate where we've got very high level of groundwater pushing up that will make it hard for them to operate, or very high levels of groundwater salinity, for example. And so here's some examples of them here, again showing the sort of the flexibility in urban form. And from my point of view, a system that can look like this, and for most people it's just an attractive garden, is a real winner, because people will be happy that there's been investment in this, even if they don't understand the technical purpose for it. They can be street tree pits like we've seen before, for example, so very flexible. A related but also quite different system is the sand filter or media filter. These are relatively cheap. They tend to be fairly space efficient because they're often underground and they have high flow rates, so they can be pretty space efficient. But they need regular maintenance because you don't have any vegetation doing that sort of maintaining of permeability. Instead, you have to scrape the top layer off frequently. So they're not really about aesthetic or amenity benefit. They're not multiple benefit. They're really about treating highly contaminated runoff from industrial or highly polluted areas. Buffer strips and vegetated swales. These are, again, a system I like a lot. In part, I like them because they can be very simple. This one here looks pretty detailed and perhaps fussy, but also aesthetically really nice. I must say I like it, and this is a site I know well. They are nice because, as I say, they can be designed simply. They provide the conveyance system, so they potentially can reduce costs a lot. And I know I've been involved in a lot of projects where the developer, who wasn't very supportive of water-sensitive urban design, was very supportive of swales because the reduced excavation costs made it very cost-effective for them. They don't tend to work so well on really steep slopes, or at least they're hard to get right. You have to do a whole lot of things like check dams to make them work, and they're difficult. If they're on really flat slopes, then water tends to sit around, so they may need some sort of infiltration component, which can be done just to make sure that you don't get sort of bogging up areas and attraction of mosquitoes. Ponds and wetlands, again, really aesthetically appealing. They work well, both for particulate and dissolved pollutants. I think they are one that developers tend to, and landscape architects tend to really like. They're quite flexible in the sense that they can provide easily a flood detention capacity, and often they're built into the bottom of a flood detention basin. They also potentially are good stores for stormwater harvesting. Interestingly, they're really good habitat for wildlife, but that can be a conflict because they can attract wildlife that then affects their water quality function. So that can be complicated. Here's an example, a site I know quite well in Melbourne, where you can really see the sort of aesthetic and public recreation benefit, or public passive recreation benefit. Infiltration systems are really appealing because they help to manage that flow regime, help to release, to recharge water into the groundwater, which can be really important. They can be, again, very flexible. They could be a porous pavement or a constructed system, or a rain garden type system can work as infiltration. So those bioretention systems we talked about before can also work as infiltration, and often do. They can be very simple, or they can be subsurface. They can be a trench sort of system, for example. Another system that's really appealing is the rainwater and stormwater harvesting sort of systems. These have the benefits of providing a water supply, which reduces the potable water demand, reducing the peak flows and reducing the overall flow volume, but also reducing the load of pollutants, because every bit of water that's taken out is taking out some pollutants with it. They're very flexible and scalable. You can get tanks in all sorts of forms. They can be above ground, underground, and they're very well suited to urban areas. We need to think about their costs. They can be fairly expensive, and we need to think about how the water quality is going to match how much treatment we're going to need and what cost and energy cost that'll have. And indeed, there are some kind of energy-water interactions to consider. For example, using high efficiency pumps is going to make a big difference. There are really big differences in the energy use of different pumps. And with the much greater availability nowadays of variable speed pumps at the smaller scale, we can get energy use right down, but these things tend to have higher capital costs. So these are things to think about.